afternoon. Okay, let's start our physics lesson, which is about the motion of a body maybe around a planet. Okay, in last lessons we have seen that there is an attraction force between two bodies, and this attraction force is that a force that exists between two bodies due to their mass, and the magnitude of the force depends on the product of the two mass and inversely proportional to the separation distance square. Due to this force, when an object is moving around maybe a huge object or a big object, then it gets a support force just to follow it or to move around it. And one of these concept is orbital velocity of a satellite. For example, there are different planets that move around the sun, and in similar way, there are different satellites that moves around the planet. As you know, there is a fixed point. For example, in a solar system, there is a fixed point which is sun, and a number of planets will move around the sun. And in similar way, planets have satellites. But the number of satellites depends on the types of planets. But despite all planets except a few, most planets have satellites, maybe one or more than one. For example, for Jupiter, there may be 13, about 13 satellites. But for Earth, there is a number of satellites, but the satellites may be natural satellites and artificial satellites. Earth has only one natural satellite, which is Moon. For example, we do have Earth, and then there is only one and a big satellite, natural satellite, which is Moon. But not only Moon. There are a number of satellites that revolve the Earth, which is called artificial satellite. This Moon is a big one and natural. You can say these points about the Moon. Moon is one of the natural satellites, which is a big and natural satellite of the Earth. But not only Moon, there are a number of satellites that launched by human, and we call it artificial satellites. And these satellites has different purpose. For different purpose, human are launched these satellites, and has the same nature with the Moon. Moon revolves the Earth, and those artificial satellites also revolve the Earth. They move around the Earth. Therefore, there are a number of satellites that orbit the Earth, whether they are artificial satellites or natural satellites. But Earth has more than one satellites that revolve it. But the satellites are, some of the satellites are artificial satellites, and the others, especially, there is a unique satellite which is called Moon that moves around the Earth. And this Moon or any other satellites have an orbital velocity or has a velocity that used to move around the planets. For this case, for this particular case, the satellite is Earth, and the Moon and the other artificial satellites are revolving or orbiting the Earth with an orbital velocity. And to get the expression for this orbital velocity, we have to think that the orbital path of the moon is nearly circular. The path is nearly circular. So we can take it as a circular path, not elliptical. We know that the real shape of the path is elliptical, but for mathematical simplicity, let's think that the path is circular path. And the moon is rotating the Earth. When the moon rotates the Earth, there is a centripetal force or central force, which is centripetal force. And the expression for centripetal force is mass of the moon times tangential velocity square of the moon over distance between the moon and the Earth. This is the centripetal force that supports a moon to rotate around the Earth. And the other force, the other possible force, maybe has the same magnitude with the centripetal force, is gravitational force between the Earth and the moon. And this gravitational force has an expression, as you know, is gravitational constant times mass of the moon times mass of the Earth over separation distance square. The separation distance is a distance between the center of the Earth up to the center of the moon. Therefore, we have these expressions. By default, these two forces are the same, or they have the same value. So we can equate it. Since the centripetal force and the gravitational force is equal in magnitude, even though we give the different names for this value, but the value is the same. So we can use it, or we can equate it. Then here, the same expression can be cancelled from both sides. For example, we can cancel mass of the moon from both sides, and we can simplify one radius, and we left with v square equals gravitational constant times mass of the Earth over a single r. Then just to express this velocity alone, then it becomes g times mass of the Earth over r. Then we have to put under radical. And this expression is called an orbital velocity of the Earth, or simply the tangential velocity of the Earth, the tangential velocity of the Earth, the tangential velocity of the moon when the moon is rotating the Earth. This is the velocity of the moon as it orbits the Earth. Therefore, this is the velocity of the moon when it moves around the Earth. Then this value depends on three quantities. The first one is gravitational constant, and the other one is the mass of the Earth, and the other one is the radius between the center of the moon up to the center of the Earth. So these three quantities are constant. It doesn't depend on a certain situation, which is constant. Then we can say that the value of the tangential velocity of the moon when it is moving around the Earth depends only on the mass of the Earth, the gravitational constant, and the separation between the moon and the Earth. Therefore, we can get a constant value. For example, let's see in example 4. Find the speed of the moon if the mass of the Earth is approximately 6 times 10 raised to 24 kilogram, and the distance from the moon to the Earth is 4 times 10 raised to 8 meter. And we know that the gravitational constant is known, so we can find that the tangential velocity of the moon when it's moving around the Earth. Not only for a moon it holds true for any satellites that launches near to the surface of the Earth. We have given quantities. The first one is gravitational constant, which is given 6.67 times 10 raised to minus 11 Newton meter square over kilogram square. And the other quantity is mass of the Earth. Capital M equals approximately, this value is taken as an approximate value of the mass of the Earth, which is 6 times 10 raised to 24 kilogram. And the distance from the center of the Earth up to the center of the Moon is determined to be 4 times 10 raised to 8 meter. And what we are looking to find is the speed of the Moon when it is orbiting the Earth. Then V becomes square root of capital G, gravitational constant, times capital M, mass of the Earth, over radius between the Earth and the Moon. Then we can substitute the values. 6.67 times 10 raised to minus 11 times mass of the Earth is 6 times 10 raised to 24, because all quantities are in standard form. You can simply substitute. And the radius is 4 times 10 raised to 8. Then when we do this, we get 1000 meters per second. Meter per second. There is an error on your textbook. It says 1.0025 times 10 raised to 14. Not 14, but it is 3. The power of 3. It's approximately 10 times 10 raised to 1 times 10 raised to 3 meters per second. Not 14, but it should be 3. So this is the tangential speed of the Moon around the Earth. And the other point, as you know, the Moon takes maybe a constant period when it is moving around the Earth. And there are different satellites, especially there are satellites that we call geostationary satellites. Why we call a geostationary is when we're looking at the satellites, they are always on the head of, they always seems to be there. They are always in the same spot in the sky. When we are looking to the satellite, they are always in the same place. Even though they are just rotating the Earth, since we are also rotating the Earth, then it seems constant. So these geostationary satellites are satellites that orbit the equator with the same angular velocity as the Earth. As you know, the angular velocity of the Earth is 2 pi over period, and the period of this Earth is 24 hours. Then the orbital velocity remains constant, which is 2 pi rad over t, where t is 24 hours per day. And they're used for communication. The purpose that launched this satellite is mostly for communication purpose. They used for communication purpose, for telecommunication, or for mobile technology. Not only for this one, even they help us to determine the location of minerals or any other resource, natural resource. They tell or they give image about the location of natural resources like minerals or any other forms of natural resource. So the purpose of this launching satellite is generally for communication purpose, but it depends on the purpose. We may use for military purpose, or sometimes it is used for agricultural purpose or for communication purpose. But what we need from satellite is they send signals and they facilitate the communication world. The other point that we need to mention here is the escaping velocity of a satellite. Satellite needs to escape from the Earth's potential, need to be clean out of this potential or from atmosphere, because they revolve the Earth after being a certain height from the Earth. They need to be clean out of this Earth's potential or Earth's gravity. When they are initially launched with a high kinetic energy, then they will be out of this potential. Then after getting a certain height, they start to rotate in a horizontal direction. But before that, they have to be clean from the Earth's potential. Then this kinetic energy is an energy that is given to a satellite to move from the atmosphere. And this potential energy is the energy of the Earth that challenges the satellite not to move out of this atmosphere, which is mass of the Earth times mass of the satellite divided by the radius from the center up to the location of the satellite. And in a similar way, we can cancel mass from both sides. As you know, when we are driving expression for speed, we have used centripetal force and gravitational force, which is G times M over R. But here we have used energy approach, or we have equated the kinetic energy with potential energy, because this kinetic energy is needed by a satellite to escape from Earth's potential. Then now we can cancel M from both sides. Then after cancellation, then if we multiply both sides by 2, we get V square equals 2 times G times mass of the Earth divided by radius of the Earth, or distance from the center of the Earth up to the location of the satellite. And let's multiply for simplicity to get a simple expression. Let's multiply by R from both sides, and we get 2 times G times mass R divided by R square. And we remember that G times mass of the Earth over radius of the Earth square is gravitational constant. Then we can insert into our expression to get 2 times gravitational acceleration and times radius of the Earth. Then finally, when we left V alone, then we have to insert into a radical sign, and 2 times gravitational acceleration times radius of the Earth square. And this velocity is called escape velocity. Velocity that's needed to move a satellite out of the Earth's potential. So this one is the velocity, or just like kinetic energy, which is given for a satellite to escape from atmosphere. Then after arriving at a certain place, the satellite moves with a zero energy, or simply moves with a uniform circular motion, or simply move with a uniform circular motion without having an energy. And let's say this, find the escape velocity for a satellite leaving the Earth. This is common for any satellite. If you need to launch satellites, then we don't need to consider the mass of the satellite. What we need to consider is the radius of the Earth. But as you know, the radius of the Earth is not constant at any point on the Earth. I think you remember it is not constant on any parts of the Earth. For example, it is nearly maybe large at equator, whereas it is slightly less at a polar region. So it's better, sometimes it's better to launch satellites at equator than a pole. Then here, find the escaping velocity of a satellite leaving the Earth. The radius of the Earth is approximately 6.4 times 10 raised to 6 meter. And gravitational acceleration is nearly 981 meter per second square. And we're looking to get escape velocity. Then to get escape velocity, simply we use 2 times gravitational acceleration times radius of the Earth. And it becomes 2 times 9.81 times radius of the Earth is nearly 6.4 times 10 raised to 6 meters. Then this value is it is 11 kilometers per second, which is very known speed, 11 kilometers per second. By the way, this is common for any satellite. If you need to launch satellite, then the satellite need to give, or we have to give a speed which is 11 kilometers per second for a given satellite, respective of its mass. This is the very known value for any satellites. The escaping velocity from the Earth is 11 kilometers per hour. But this value is not the same for any planets. If you need to launch from Jupiter or from Saturn, then things will vary, because this is particularly for a satellite that is launched from the Earth, not from other planets, but from the Earth. And let's summarize the point that we have discussed today. The first point that we have tried to see is orbital velocity of a satellite. The Earth has large number of satellites in orbit around it. There are 2 kinds of satellites that orbit the Earth. For example, as you know, Earth rotates the Sun, and there are different bodies or different planets are rotating the Earth, the Sun, and in a similar way, there are a number of satellites that orbit the Earth. But the satellite is divided into 2: the artificial and the natural satellites. So the natural and the artificial satellites. For example, the only natural satellite is Moon, and which is the biggest one. Not only the natural, but the biggest one is the Moon. And there are artificial satellites that launched by human for different purposes. It depends on the desire of the country. And to get the velocity of a satellite when it is rotating the Earth or any planet is obtained by equating the centripetal force with the gravitational force. As you know, the centripetal force of any object, the net force for any object which is moving in a circular path is mv square over r. This mv square over r is the centripetal force or the net force for a body that follow a circular path. But let's assume that the moon is following a perfect circle. Even though it's an elliptical path, let's think for this case that the moon is moving with a circular path around the Earth. Then this mv square over r is equal to the gravitational force between the moon and the Earth, which is g times mass of the moon times mass of the Earth over separation distance square. Then we can cancel common quantities because there are common quantities. Mass of the Earth is not common because not in the left expression, but mass of the moon is common. So after simplification, we arrive with v square equals gravitational constant times mass of the Earth over separation distance. Then when we just make v alone, it becomes capital G times m over r. And this is not an orbital velocity and not skipping velocity, but this is a velocity that's used by the satellites when they are moving around the Earth. This is the velocity, and by using this velocity, satellites will be in a circular motion or in a uniform circular motion. And this value can be obtained in the case of Earth. For example, find the speed of the moon if the mass of the Earth is approximately 6 times 10 raised to 24 kilogram, and the distance from the moon to the Earth is known, which is 4 times 10 raised to 8 meters. Then after having these quantities, we can determine the value of the velocity that a satellite used to revolve around the Earth. And the velocity becomes approximately 1000 meters per second. So when the moon is rotating around the Earth, it covers 1000 meters in a second, which is the very fastest speed. It's one of the fastest speed. Just the moon used to move around the Earth. And not only moon, there are a number of satellites, which is called geostationary satellites or artificial satellites. Artificial satellites are called geostationary satellites because these geostationary satellites, they seems to be stationary. When we are looking at the satellites, they are always on the same spot, and we may consider them as stationary because no change on their point. Because they are on the same point, since you are revolving with the Earth, we're looking them at the same point. So they are said to be geostationary satellites, and they move with the same angular velocity as the Earth, which is 2 pi over t, where t is the time for one day, which is 24 hours. And they're always in the same spot in the sky. They are used for communication purpose. Most of the time, they are human-made satellites, and the purpose that launched above the Earth is for communication purpose, not only for specific communication, but for maybe military purpose, or it may be for just identifying the location of minerals or natural resource and the like. The other point that need to point out is escaping velocity of a satellite. A satellite needs to escape from Earth's potential just before arriving at their stationary point. They have to skip or move out from Earth's potential or out of atmosphere. Just to be clear, out of atmosphere, they have to get a kinetic energy, an enough kinetic energy, and this kinetic energy must be equal to the potential energy. Kinetic energy is an energy that a satellite used to move up, whereas potential energy is just like an opposition part or in opposite direction. Then the kinetic energy, as you know, is 1/2 mv square, and for potential energy, it is m, which is gravitational constant times mass of the Earth times mass of the satellite over r. Then we can cancel m from both sides. Then after cancellation and after multiplying both sides by 2, we get v square equal to gm over r. And to get a very simple and known formula, which is 2gr, let's to get this expression, let's multiply by r over r. R over r, as you know, is 1. Then it becomes 2gmr over r square. Then from previous knowledge, we know that this gm over r square is acceleration due to gravity. Then the expression has been reduced to square root of 2gr. Therefore, the escape velocity is 2g times r. For example, for a satellite that leaves the Earth, the escape velocity is 11 kilometers per second, which is the very known expression. So we have to bear in mind that the orbital velocity of a satellite is 2 pi over t, where t is period. T is period of the Earth, and the other one is a velocity of a satellite that moves the Earth. That moves the Earth equals square root of gm over r, and the last one is escaping velocity. Escaping velocity of the Earth is 2g times r. This one is escape velocity, and this is orbital velocity. Orbital velocity is similar to that of angular velocity, and this one is speed used by a satellite when it moves around the Earth. So these are some of the velocities related with a satellite moving around the Earth. Okay, do you have any question? Okay, if you don't have question, thank you very much.